Another component of heat in chemistry is referred to as calorimetry. We've talked about calories lowercase c and calories with an uppercase c, the difference between calories and kilocalories. Uh, Calorimetry is a technique that we use to measure the amount of heat that's involved in a chemical or a physical process. It How it works is it allows a substance to undergo a reaction or a phase change in contact with a calorimeter. And calorimeters are devices that measure the temperature change. And then from that temperature change, we can calculate the amount of heat that has been transferred. To In order to do calorimetry correctly, we have to define some things about how we measure heat. The system is the substance or substances that are undergoing change, and the surroundings are everything else that can absorb or release heat. The heat that's lost or gained by the system is exactly balanced by the heat that's gained or lost by the surroundings. And that's assuming that no heat is exchanged with the internal or with the external environment, excuse me. So what a calorimeter does is it isolates the system from the external environment. This way, any heat transfer that occurs is only between the system and its surroundings. In exothermic reactions, the heat released by the reaction warms the surrounding solution. And in an endothermic reaction, the solution provides the heat, which drives the reaction. And here we have a diagram that shows us both exothermic and endothermic processes. So figure A shows us an exothermic process where heat is flowing from the system to the surroundings. And in this case, Q, our measure of heat, is negative. For diagram B, we can see that this is an endothermic process. Heat is flowing from the surroundings to the system, and Q is a positive value, so heat is a positive value. And the system's temperature change reflects the direction of the heat flow. A calorimeter has to be insulated, and that prevents heat exchange with the external environment. A simple calorimeter is constructed out of polystyrene cups. A lot of times in laboratory settings, when you're learning about calorimeters in school, you'll use just two styrofoam cups. That's fairly common in lab settings. And then we have commercial calorimeters, which are much more advanced, and they're used in research or industry for better precision. But in either way, the goal is to capture all the heat that flows in a reaction. So this shows a simple calorimeter, and the two cups here, there's two of them to help to insulate it a bit more. There's a thermometer and there's a stirrer that extends through the lid, and the reaction is what's happening on the inside of the container. And the setup prevents heat exchange with the air, and it makes it a good low-cost option for using or for checking calorimetry in the classroom. So we looked at two different examples, or I mentioned two different examples. We have a basic student calorimeter, and then a precision instrument used in the industrial or research settings. Um, this is a more simple, inexpensive model, so we might see these in the classroom also. They're not necessarily styrofoam; they have metal on the outside. They have a metal inner vessel, and there's this supporting ring here, and then there's a stirrer, and then of course the thermometer to check the temperature. Um, Again, we use these more accurate models for industry and research. You can see the motorized stirrer, so it's connected to something that stirs it, so to keep the heat evenly distributed within, so we can get very accurate measurements. And it's most likely more insulated than just a basic calorimeter. Calorimetry principles. If we place a hot metal object into cold water, we can say that the metal M will lose heat and the water W will gain that same amount of heat. Eventually, both reach the same final temperature. So no heat escapes to the environment. It's just metal and the water exchanging energy with one another. And they'll reach that equilibrium, which we discussed earlier in the lesson. In a perfectly insulated calorimeter, the heat lost by the metal equals the heat gained by the water. So we can write that as Q of the metal plus Q of the water equals 0. And this says Q substance metal, same thing as QM or QW. They just wrote substance here on this slide, but the basic idea of total heat from metal plus total heat from water is equal to 0. If we rearrange this formula and now set it so it's not equal to 0, we can say that the heat of the metal is equal to the negative heat of the water. And the sign tells us which substance is gaining the heat and which substance is losing the heat. In this next figure, this shows thermal equilibrium. Figure A, the hot metal transfers energy to the cold water. And in figure B, eventually both of them reach the same temperature. This is called thermal equilibrium, when no more heat flows because both objects are at the same temperature. Let's look at an example with some numbers next. So there's a 360 gram piece of rebar. It's placed into 425 milliliters of water at 24 degrees Celsius. The final temperature of the water is measured to be 42.7 degrees Celsius. And we want to know what the initial temperature of the rebar is. Now, in order to do this, we have to know some things about the specific heat. Earlier, we talked about the specific heat of water, and we can look that up in our textbook. But we also have to find the specific heat of iron. So the rebar is steel, and we're going to just assume that it's about the same specific heat as iron. So the specific heat of iron is 0.449 joules per gram degree Celsius. And water has a density of 1 gram per milliliter. And this is 425 milliliters of water. So there's 425 grams of water. So we're trying to find the initial temperature of the rebar. So the water increases in temperature. That means that it absorbed heat. And the heat must have come from the rebar, which cooled down. So the heat given off by the rebar is equal to the negative heat taken in by the water. So we can plug in these values using our equation for heat. And the equation for heat is Q equals Cm delta T. So we're going to put Cm delta T of the rebar equals negative Cm delta T of the water. And to find delta T, that's final temperature minus initial temperature. And in expanded form, it looks something like this here. Now we're going to begin plugging in some of these values. So we're going to substitute in our known values. So our, our specific heat of water, they didn't tell us in the problem, but we do have to look that up. It's 4.184 joules per gram degree Celsius. The mass of the water is 425 grams. The mass of the, I'm just going back here to our question, the mass of the rebar is 360 grams. So we know M for rebar and M for the water. We know specific heat for rebar is the same as iron. We just look it up for what iron is. It's 0.449 joules per gram degree Celsius. And then our specific heat of water, 0.449 joules, or excuse me, the specific heat of water is 4.184 joules per gram degree Celsius. Our final temperature of the rebar is 42.7 degrees. Our final temperature of the water is also 42.7 degrees, and that is because they've reached thermal equilibrium. So we plug all of these values in, and we want to find the initial temperature of the rebar. And all we're doing here is we are just solving algebraically for the initial temperature of the rebar. So you would multiply these two values first, or what might even be easier than that is just divide this and this on both sides. Then you're left with just 42.7 degrees Celsius minus the initial temperature of the rebar equals all of this divided by these two terms. And then we would just subtract 42.7 on both sides. Now we have double negatives, and we would just multiply by -1 on both sides, and it would give us 42.7 degrees Celsius. So a little bit of algebra that we have to do there. I didn't write all the algebra steps out, but I think that if you are taking this course, most likely you'll be okay with these algebra topics. So solving this equation, the initial temperature of the rebar, we get a final answer of 248 degrees Celsius. And so that is the initial temperature of the rebar. When we use calorimetry to determine the heat involved in a chemical reaction, the same principles we've been discussing apply. So in a reaction, the heat of the reaction plus the heat of the solution equals 0, or Q reaction plus Q solution equals 0. This means that if the reaction releases heat, the solution absorbs it. If the reaction absorbs heat, the solution loses it. So Q reaction is negative Q of the solution. And when we solve that, when it was originally set at 0, but we can just move that to the other side. Now we have a general rule for calculating heat. So this is a fundamental equation that we use in calorimetry problems. We often measure temperature change in the solution and then use that to calculate the heat of reaction. Let's look at another example. This is hydrochloric acid and sodium hydroxide. So when 50 milliliters of a 1 mole hydrochloric acid solution and 50 milliliters of a 1 mole sodium hydroxide solution, both at 22 degrees Celsius, are added to a coffee cup calorimeter, The temperature of the mixture reaches a maximum of 28.9 degrees Celsius. What is the approximate amount of heat produced by this reaction? So we have 50 milliliters of each of a 1M solution for both of these. The temperature ends up going to 28.9 degrees Celsius, and we want to find the heat produced by this reaction. So here's the balanced reaction. It gives us that part. That's great because sometimes it doesn't always tell us the balanced reaction, but in this case, it does. So to visualize what's happening, we combine these two solutions. Imagine you could combine them so quickly that no reaction took place while they're mixed. After we mix them, a reaction takes place. Once that mixing happens, now we have 100 milliliters of a mixture of HCl and NaOH, both at 22 degrees Celsius. The hydrochloric acid and sodium hydroxide then react until the solution temperature reaches 28.9 degrees. We're going to use this same basic equation of the heat of the reaction equals the negative heat of the solution. So we know the specific heat of water. We know the total volume is 100 milliliters. And the density of water is 1 gram per milliliter. So these are both aqueous solutions. So the total mass is 100. And the specific heat of water, again, is 4.184 joules per gram degree Celsius. So our total solution is what it is when it's mixed together. That's the total solution. And the heat of our solution equals specific heat times mass times change in temperature. So we're going to write specific heat of water here. The total mass, when they're combined, they form 100 grams altogether. And then the change in temperature. So let's go back to our problem here. It changed. It started at 22 degrees Celsius and it ended at 28.9. So we're going to subtract 28.9 from 22 to get our change in temperature. And here's what all those values look like when we plug them into our Q equals MC delta T equation. Here's C, here's the mass, and it's written as scientific notation. And then here's the change in temperature, and we get a final answer of 2.9 times 10 to the 3 joules, or 2,900 joules. But we want to find the heat of the reaction. So we found the heat of the solution, but the heat of the reaction is the opposite of that. So the heat of the reaction is the negative heat of the solution. We found the heat of the solution, but we want the negative heat of the solution. So we're going to do negative 2.9 times 10 to the third joules, or negative 2,900 joules. So what this negative answer means is that the reaction is exothermic. It produces about 2.9 kilojoules of heat. Hand warmers uses an exothermic reaction to produce heat. When it's activated, it warms up very quickly and it releases thermal energy to your hands. And this is just an everyday example of how we can apply thermochemistry in our day-to-day lives. We also have cold packs that contain ammonium nitrate and water in these separate compartments. When you break the seal, the two mix and they absorb heat, and that creates an endothermic reaction. The pack becomes very cold and it pulls heat from your body heat in order to make the pack cold. A bomb calorimeter is used for reactions that release large amounts of heat and gaseous products like combustion. Reactants, they're placed in a steel container, and we call that the bomb. And then the bomb is submerged in water. The heat released, it warms the water, and the temperature change is measured. And here's what a bomb calorimeter looks like in laboratory settings. And again, we can measure heat in reactions that are combustion reactions. So this is all for capturing heat from high energy reactions. We also have things like that are called whole body calorimeters, and they're actually large enough to hold an entire person. They measure total energy use and the effects of different diets or health conditions that people might have, such as diabetes. Energy is usually reported in calories uppercase C, again, where one uppercase C calorie equals 1,000 lowercase c calories, or 1 kilocalorie with lowercase c. And again, our calories and our food labels, we have calories written here. These are all in kilocalories. This is just another everyday application of calorimetry, and we can see how much chemical energy that we're getting from our food. All right, and here are the questions associated with this section.